Well, thanks for coming today. I appreciate it. This session is kind of a new one for me, meaning that for this NASRC, I normally have a different presentation that I do for NASRC. It was on walking through a P&ID diagram of the Copeland mobile trainer that you'll see out there. There is a session, 2 sessions a day about the mobile trainer and you know, some of the basics of CO2 refrigeration and using the trainer as an example. So prior to this, I was doing the P&ID and kind of walking through it. And you'll find that a lot of the sessions over the next 3 days, there's a lot of, you'll be walking through the cycle a lot, and there'll be a lot of repetition, but a repetition as far as CO2 is concerned, something if you're not that familiar with it is a good thing. You do really have to listen to it, hear it, explained in different ways by different speakers for it to soak in. At least for me, that's the way it's been for me. So take advantage of it as much as you can. In my presentation today, the reason I decided to do this is because I was asked to do a presentation for 60 service techs in Canada a couple months ago. And it was all service techs that worked on a specific retailer store. So they asked me to do this particular presentation, and it was well received, and I was invited to do it to other contractors. So I thought maybe it would be a topic that would be of some value here today. So that's why I'm doing this particular presentation. Before I get into it, there's a couple of key things that kind of from a basics perspective. And when you ask yourself, you know, CO2, why are we talking about CO2? Obviously, it's because of global warming that's happening, but these are things that we live with on a daily basis. You know, household garbage can create 1 metric ton of carbon emissions. Kind of brings it closer to home. If you're driving a car at 23 miles a gallon for 2,700 miles, it's 1 ton. You know, and if manufacturing of cement, if the cement industry was a country, it would be the 8th largest producer of carbon emissions in the world, kind of give you a scale. So that's one thing. The other thing, if you watch the Super Bowl, you probably heard a lot about Taylor Swift coming from, you know, Japan, flying from Japan all the way to Vegas, and her carbon footprint and all that kind of stuff. So I decided to do a little research. Really, what kind of carbon footprint does she really have, or anybody else? I'm not picking on Taylor Swift, but it was a hot topic at the time, so I did a little research. So it says Swift traveled 37,000 miles, generating 77 tons of CO2 emission from a private jet, 113 flights. So I wanted to understand, what does that mean when you equate that to refrigerant? 39 pounds of leaked 404A is equivalent to that 75 metric tons. Think about that. We got a 2,000 pound system, potentially of 404A, and it could leak, according to EPA, 25%. That's 400 pounds. That's 713 metric tons. That's almost 10 times more than that jet traveling 113 times. That's why our industry was targeted. It's a massive number. So I just wanted to kind of put that in perspective. So some of the CO2 system, the booster system, I'm going to just quickly walk through the circuit to kind of get us grounded before I start getting into high pressure valves and bypass valves and oil systems. Because I just like to explain it the way, you know, my head works. CO2 systems run on, when you look at any CO2 system, you're using, the CO2 is kind of used in all of the medium temps as well as all the low temp cases. And when you look at this chart, there's 4 colors on it. And those 4 colors also represent 4 different pressure zones of the system. Your discharge can range from 700 to 1,500 pounds. And it's typically stainless steel or XHP, high pressure ferrous alloy copper, right? Now you get into, through that high pressure valve, which is nothing more than an electronic expansion valve that's rated to 2,000 pounds of pressure. And as an expansion valve that expands that fluid to a lower pressure, because we need a lower pressure in the flash tank, just like we need a lower pressure in our evaporators, so we need an expansion device to do it, specialized expansion device. And let's say, for sake of argument, we're gonna have 520 pounds in my flash tank / receiver, okay? So all the yellow here is another pressure zone. It's liquid, and it's liquid at around 35 degrees. So of course everything has to be insulated. Your flash tank, your liquid line is 35-degree liquid, somewhere in that range. That's enough pressure zone. And this is typically protected to 650 PSI today. Currently, pressure relief at 650 pounds or 545 bar. We get into the low temp side of the system. Typically today in North America, the standard's around 30 to 35 bar, which is around 500 PSI. Another zone. The green is my medium temp suction, and it's also protected to about 650 pounds or 45 bar. So 4 different zones, yeah. This one and this one is protected to the same pressure relief today. There's talk about what do we need to do to get it higher. On industrial systems already, everything blue, yellow, and green is 90 bar in a lot of industrial jobs. 90 bar, 1,305 pounds. And the supermarket industry is thinking about what do we need to do collectively to go from 650 pounds on my liquid and suctions to maybe higher so we don't have release events. I don't know if you've heard the term release events, but release events is an event where you have a significant amount of refrigerant that blows off through a pressure relief valve. Not a leak on a joint, pressure relief valve. That's a release event where now you got to go look for refrigerant. You know, they want to avoid that because sometimes if you can't get refrigerant for a day or two, you're losing everything in your store. So that's not a good thing. And that could be hundreds of thousands of dollars. One retailer was saying he had a release event. The entire store was about 45,000 square foot store. Couldn't get refrigerant for 2 days, cost $400,000 in product. Kind of give you an idea. So that's why those conversations are happening. So booster system, discharge through the high pressure valve, liquid, but you can see here, liquid's feeding my medium temp cases to my medium temp suction. Low temp goes to my low temperature compressors, and they're discharging into my medium temp. So I've got 3 sources of mass flow going to my medium temp compressors, from the low medium temp cases, from my low temperature compressors, and from my bypass valve. And I'll talk a lot more about the effects of that in a few minutes. So that's really the basic system. We are operating higher pressures in the summer when we're hot outside. A lot of climates, though, you're not operating below, you're above 87.8 degrees. In many climates, you're operating below that point. This is our critical point of 87.8 degrees, and you'll hear a lot about that today and the importance of it, but that's low. 404A is like 162 degrees. You never get to 162 degrees. But on CO2, you can reach that point of 87.8 degrees on a hot day. This week, as a matter of fact, I was on a roof yesterday. It was 83 degrees. So that system was operating in supercritical mode, above the critical point. The other thing that's interesting about a CO2 system, look at the pressure ratio versus 448A. You're going from about 200 pounds suction, 400 pound suction, medium temp, to up to 1,500 pounds. That's like 5 to 5.5 times higher than an HFC system. So that's why your compressors are built very differently. Much heavier duty to handle those bearing stresses and high loads, okay? So that's another thing that's unique from a pressure perspective. So where does a high pressure exist? It exists in the discharge at the outlet of my compressors, up onto the roof, into my gas cooler or condenser, and then back to the high pressure valve. That's really where it stays. The rest of the system, all those line sets, you're not seeing high pressure in there. It's all liquid line pressure, suction line pressures, or discharge to the low temp, which is the same as medium temp suction pressure. So those discharge pressures are isolated, okay? And because of those pressures, of course, as I mentioned, compressors are designed to manage those high pressures. Most of them can operate up to 1,740 pounds or 120 bar. You got pressure, high pressure piping. Type K is used a lot to manage up to 650 pounds, those zones. But when you get up into the discharge, then you're moving up to type XHP, which is a ferrous alloy copper or stainless. And then you've got to make sure you of course, evacuate to get all that moisture out, because moisture is also very dangerous in a CO2 system, as it is in any system, where you can get carbonic acid damaging a lot of components. And pressure relief valves, depending on where you are in the state, your codes may be a little different, so piping them, bringing them outside, how far off the roof, all those things may vary depending on the application, depending on where you are. And just real quick, we call them transcritical systems because the pressures can transition, like a day like today that is cool in the morning and it warms up above 80 degrees, transition to supercritical operation, and then transition back to subcritical. That's really the reason we call it that. So I'm just going to go through this chart, and I'll get into the rest of the presentation. This is a chart I like to use to kind of walk you through the schematic, starting at the medium temp compressors. Number one, discharge. And you can look at the enthalpy diagram, the pressure enthalpy diagram in BTUs per pound down here. We're starting at 0.1, which is about 20 degrees saturated suction medium temp, discharging into the supercritical zone at about 240 degrees, 0.2. 240 degrees goes through the gas cooler / condenser. We call them both because it condenses below 87.8. But in this particular case, it's not condensing, it's only reducing it from 240 degrees to 100 degrees. So it's taken 140 degrees of superheat off that gas, but it's still a supercritical fluid hitting the inlet of that valve. We know that we need liquid in the flash tank in order to feed my cases, so I've got to drop that pressure 3, and as I drop that pressure, you can see the pressure drop, there's flash gas that's created because this is my saturated liquid line, this is my saturated vapor line, and I've got a two-phase mixture in the middle. The closer we get to the center, we've got a 50-50 liquid and vapor. So I've got close to a 45% vapor in there, right? And then I've got liquid in my flash tank that feeds all my expansion devices. So I've got 520 pounds here, and I've got 400 pounds here. I've got a 120-pound pressure drop across the valve. And when you're sizing these expansion valves, the head pressure is not this head pressure. When you look at a sizing chart, when you want the inlet pressure is your flash tank pressure. It's a little bit different way of thinking because that is your inlet pressure. So you go through the evaporators, one mass flow going into my suction. My low temp, I've got 200-pound suction, 520 here. I've got 320-pound differential, which you've got to size that valve for that differential. And then up here, when we're trying to maintain the flash tank, this valve, this bypass valve, opens and closes. If the pressure is too high in the receiver flash tank, the valve opens, and when the valve opens, there's a mass flow that goes into my medium temp suction. I like to call that taxes you have to pay. If it's cold out and you're condensing subcritically and you're right here in the condenser and you go through the high pressure valve, you have very little flash gas. You're not paying many taxes. As you get a situation like this, you've got a greater percentage of flash gas, That means you've got to open this valve even wider, and you're sending more mass flow into the medium temp, you're paying more taxes. That means you've got more compressors that have to run just to manage this bypass gas flow that does how much refrigeration? Zero refrigeration, right? So on the hottest summer day, you might have 45% of these compressors running just to manage that bypass gas. And that's a tax. You're paying energy to have those compressors run. So that's kind of a different way of looking at it. And of course, the medium temp compressors have to handle the total heat of rejection of my low temp, all my medium temp mass flow, plus this bypass mass flow that could be close to 50% on the hottest summer day. So that's the way I like to kind of walk through this chart. So real quick, compressor designs are really different because of I mentioned the pressure ratios are 5 to 5.5 times higher. On the left here, this is a standard discus 448A compressor. Well, here, 4D and CO2 compressors, a lot more bolts, heavier duty to handle those higher pressures. Crankshafts, the lobes are much wider and larger diameter. Larger diameter spreads out that bearing load across a larger surface area because they're much greater. They're like 30% larger diameter. The wrist pins as well are 30% larger in diameter. But the pistons are 45% smaller because of the refrigerant density so much greater. So small pistons, but everything else is larger to support those high bearing loads, high pressure differential. That's kind of a quick note. Copeland have 9 different medium temp compressors from 40,000 BTUs all the way up to, it says 280 here, but it can do about 300,000 BTUs at 60 hertz. And the dot represents 60 hertz capacity. So this one here, somewhere around 175,000 BTUs. And the line represents the drive. So these 6 smallest can work down to 25 hertz, up to 70 hertz, and the largest models can go 30 hertz to 60 hertz. And they're all manufactured in Rushville, Indiana, which is new for us because they used to come in from Europe. Now they're manufactured in Rushville, Indiana, in the US. And we also are launching the low temperature, high standstill version. Remember I talked about some customers want higher standstill pressures, so that low temp compressor's got to be able to handle 1,305 pounds when the system is off. So we have those in a semi-hermetic version, also made in Rushville, Indiana, and scrolls. They've been around since 2009, from 21,000 up to about 100,000 BTUs, kind of give you an idea. And you'll get these PDFs of these presentations that the NASRC makes everything available. So these are just the model numbers and the various voltages that we have, 462, 8230, and 575. And the only thing I wanted to point out is that this compressor is very low vibration and low sound, and one of the reasons is that it has counterweights. That large crankshaft has got a counterweight on the crankshaft here in green, and it also has a counterweight connected to the rotor, which is something we've never done before on any of our semi-hermetic compressors. We only typically balance them at one end, but with the CO2 compressor, it's been balanced at both ends. The other thing that's unique is that discharge plenum chamber that reduces pulsation and vibration. It doesn't go straight out the discharge line. It goes into that discharge plenum before it leaves. And also, when the oil travels through, this is a oil pump model, and it goes through the crankshaft, the holes, and goes into the connecting rods and up into the wrist pins. When it hits the back, it gets redirected into the crank. It doesn't continue on out and gets pulled in. So all that oil gets redirected, like it does at all of our semi-hermetic compressors, to avoid carryover from the suction gas. So that's one thing I wanted to point out. So I talked about superheat is one thing I want to make sure. that we cover. On HFC compressors, you've probably been hearing your entire career, 20 degrees superheat is the norm. And it is for the medium temp. It's around 20 degrees, 18 degrees, or 10K. 10K is 10 degrees Kelvin. You'll hear that a lot. And on low temp, though, it's 36 degrees. And you'll see that in our hands-on portion on day 3, we're talking about scrolls and the issues around scrolls if you don't maintain that 36 degree superheat. So you're going to see that. We've got actual compressors that were returned that you can actually see the damage that it causes. But 36 degrees is very important on low temp. And one of the things is this chart shows oil temperature at the bottom and viscosity of the oil. So oil temperature really inside that crankcase, as it gets colder and colder, that orange line designates the -20 refrigerant, CO2, and viscosity of it. And you can see as the oil temperature gets lower and lower, this is my 36 degree line, I've got plenty of viscosity. As it gets colder and colder, viscosity starts to drop. When you get down to below, around this area, you're close to flood back, you're getting viscosity that's not supporting those loads anymore, and you start getting accelerated wear. So if you're not maintaining that superheat, you're losing oil viscosity and you start getting wear. The other thing about if you go to a point where you're actually flooding, one thing with a scroll or any other compressor for that matter, if you do have a liquid mixture in that oil, the centrifugal force of a scroll, there's 2 fingers in a hole of that crank that picks up the oil. But if there's refrigerant in there, it'll also pick up CO2. And CO2 boils. So as the CO2 and oil runs up that crank, the CO2 boils off and the oil doesn't have enough push to get it up to that drive bearing. That drive bearing is the hottest spot on the compressor because all the compression happens right in this zone. All those frictional areas are up in that zone. So it's really important for the superheat. If you lose lubrication, that top bearing gets damaged. And in extreme cases, well, this is actually the compressor that I've got that I'll be showing. This is a ZOD58 CO2 compressor. It had a lot of wear. You can see the little circular patterns here. That's the surface up in here. Down this thrust surface is where what we call the Oldham coupling comes in contact with this surface as well. So there's some wear in here. And of course, our drive bearing sits right here in the middle. And this other surface there, you can see they're all scratched up, and they should not look like that when you look inside a compressor. There's been lack of lubrication there. And in extreme cases, that bearing could get sheared right off in the 3-phase compressor when it loses complete lubrication. So while that's the top bearing, this one didn't look so bad. So it had oil and CO2. That one got nothing because the CO2 boiled off by the time it got up to the top. That's really what that's showing. And that's just a animation of a digital scroll. You can see it unloading. There's no contact. When there's no contact, there's no compression, but it continues to turn at 3,500 RPM. The drive bearing, you see where all the compression's happening is the hottest spot. And these are what we call our Oldham coupling that aligns everything. So there's a lot of friction going on there, so you want to make sure you get oil up there. Yes?
Talking about superheat back at the compressors, how are they managing that? You're maintaining lower superheats down at the cases. Are they just injecting hot gas into it? Or?
They have heat exchangers, liquid to suction heat exchangers. There may be in extreme, on the medium temp, there's hot gas dumps as well that are used to manage. There's liquid injection and hot gas dump just to make sure it's not too low or not too high. Yeah.
Usually on the drop leg of the gas cooler, you'll have a heat exchanger that always goes through the low temp. You know, because if you're at, minus 20 degrees saturated, it's obviously, cooler than what the drain leg is, right? Mm-hmm.
Yeah. The heat exchangers are a good way of doing it. So let's get into what we've got here. So gas coolers I want to talk a little bit about. There's, of course, different kinds, dry gas coolers and adiabatic gas coolers. But we also refer to them, as I mentioned, gas cooler and condenser. We did a study, and we got a little pushback, but when we kind of explained why we did this, typically a gas cooler condenser TD is going to be somewhere between 8 to 12 degrees in subcritical mode when it's actually desuperheating and condensing. But in transcritical mode or supercritical operation, the TD is much lower because it's basically only taking the desuperheating the gas. It's not condensing it because it can't condense a supercritical fluid. You're just removing heat sensibly. But when you take a look at the subcritical operation, of course, you got ambient in, you've got a TD versus gas cooler outlet temperature. And the reason that we use 13 degrees is that even though that gas cooler, brand spanking new, might have been designed with a 10 degree, but there's about 10% reduction in airflow due to dirt and debris. That can increase your TD by 2 to 4 degrees. So when we did our study, we did it around 13 degree TD for subcritical. And supercritical operation, we use 7 degree TD. But that's really what it is. So that gas cooler condenser is trying to maintain that set TD based on whatever ambient it happens to be outside, especially in subcritical mode. So ambient temperature important, TD, and that gas cooler out temperature sensor, super important. It's probably one of the most important temperature sensors on the system. Ignacio, would you agree?
Yes, absolutely.
Yeah, we were funny because I was at a job yesterday and we were looking at the gas cooler sensor, which was interesting, and we had a conversation. I was with Brent Cheshire about, well, one OEM puts it here and the other one puts it there, and kind of, what do you think, Andre? And so it was kind of interesting, but another colleague of mine was at a different job site where the sensor was just kind of hanging there, black, tie wrap, exposed to the heat of the sun. That sensor is driving the gas cooler fans, the high pressure valve, has an impact on the bypass valve, has an impact on compressor cycling, has an impact on everything. So making sure that that sensor is properly located at the gas cooler outlet, properly insulated in the right location so you don't have ambient affecting that sensor is absolutely critical. Absolutely critical. You know, some of the things, so let me just walk through a few of these points because they're important to kind of talk through. CO2 system fan speed is controlled by the gas cooler outlet temperature. Just made that point. The set point of the fan is based on inlet air temperature plus that configurable TD, which I also talked about, and is limited to the minimum maximum value, which is configurable. So if you've got a TD of 8 to 12 degrees is recommended to allow the fan speed to slow down in mild ambient to prevent powers from wasting unnecessary power. Okay, maximum gas cooler fan set point. That fan is expected to run to the maximum speed when weather gets warm. It's achieved through that maximum set point setting. So once that ambient is warm enough, you want to make sure that those fans are always running. And you may have already worked on jobs where you know that when all those fans are running full out, that your system is more stable than when they start to vary their speed. Because that gas cooler outlet temperature doesn't get a chance to change its temperature as quickly because the airflow on that coil is always the same. The minimum gas cooler set point, the minimum fan set point should not be set lower than the flash tank saturation temperature. So if my saturation temperature is 520 pounds, I sure as heck don't want my gas cooler minimum pressure to be less than 520. Because the liquid would be so cold going into it, then it's going to mess up all of the liquid going to all of your cases. And then you're going to start having controlling issues. The other thing, gas cooler should be running at maximum speed. We talked about that. The gas cooler fan should stay as close to minimum speed under cold weather conditions to maintain minimum gas cooler outlet temperature. We had a situation in Canada where the gas cooler fans were actually shutting off completely, like a fan cycling, the last one, and then turning back on. And the service techs working on it, it's just an absolute nightmare because you get all this airflow on it, and then the gas cooler outlet temperature gets colder, and it reacts, the high pressure valve, the bypass valve, the compressors. So let's kind of take a scenario and look at this. I'll be using this chart. I've only put one compressor on here. I did not put the heat exchanger for the low temp or the medium temp because it complicates the chart too much. But what I've got here is a medium temp compressor. I'm assuming 410 pounds. Oil separator, oil reservoir. This is a low pressure oil system. The oil reservoir feeds my medium temp compressor, feeds my low temp compressor. I have a hot gas dump valve, so when my superheat gets below 10 degrees, it's going to increase that, or whatever the set point is set, it's going to send a little bit of hot gas in there to make sure it's at its 20 degree set point. I go up into my gas cooler condenser, gas cooler outlet temperature, T1. I come into my high pressure valve, my flash tank set for 520. My bypass valve is here, sending it to my medium temp suction. I have a liquid dump valve should my superheat get too high. So if I don't have a lot of medium temp load and I've got a lot of low temp load, I've got a lot of discharge gas coming in here and increasing my return gas temperature to my medium temp compressor. You're going to want to de-superheat that a bit. I've got my liquid line. I'm showing one evaporator. You could have 50. And I'm showing one low temp. And you can see that my bypass valve is connected to my high pressure controller and valve driver. This valve driver, I'll talk a little bit more about, is connected to the high pressure valve, the bypass valve, and then my iPro is connected to my pressure transducer at the outlet of the gas cooler, pressure transducer on my flash tank, and my T1 temperature sensor at the outlet of my gas cooler. So those are all there communicating with a supervisory control. Now, one thing that we found out, we've been doing a lot of data analytics over the last 6 months. And because we have a data science team, and we have some of our customers are connected to our Connect Plus remote enterprise services. We've been looking at 100 CO2 stores. Which ones are working well? Which ones are not working well? Why are they working well? Why are they not working well? And looking at all that data. And at the end of the day, we've come up with some numbers that make a lot of sense, is that the gas cooler minimum pressure set point on that gas cooler should be approximately 100 PSI higher than my flash tank. So if I'm trying to maintain 520 pounds in the flash tank, your minimum condensing pressure set point should be around 620. What's even more important, our minimum gas cooler pressure, that's 620, let's say, needs to be greater than our iPro high pressure control minimum pressure. If they're reversed, you're going to be chasing your tail. So what I'm saying is this is 620, this is 520. This valve also has a set point that's controlled by the iPro. It needs to be between those two. Because if it's not, this gas cooler would be trying to maintain a pressure lower than this one wants to, and it'll be backing up. The other one's trying to get lower, the other one's trying to hold it back, and all of a sudden, every time the fans turn on, increase speed or decrease speed, it's going to affect this temperature sensor, it's going to affect the position that this valve needs to be, and they're just chasing their tail all day long. You can never get it to stabilize. So there's an order of those minimum set points are important to follow. And we've seen that. We've gone back. We've made the modifications with great success. So that's an important consideration. Gas coolers, different types of gas coolers, adiabatic pads, BAC has their own. Gutner has their own. This is a Ref Plus one. They use a misting system, so you don't need pads, but you do need a water purification system, which also it's a RO plus a UV light. So a little bit different, but they all provide wet bulb on the coil to drop the head pressure and reduce taxes. It's all about reducing taxes, right? If I can get my head lower, I don't have as much bypass gas going to my medium temp. I don't have my medium temp compressors running as much. That's all about tax reduction. California, Palm Springs, California. This is part of a climate study that Copeland did. And using adiabatic for Palm Springs, California versus not. This is based on NREL TMY3 annual weather data. So 8,760 hours a year in Palm Springs. If it did not have an adiabatic gas cooler, we know it's dry in Palm Springs, the desert, you'd be running half of the year in transcritical mode just because of ambient. But because it's so dry and the impact of water, you go from almost 4,700 hours a year to 567. Has a tremendous impact. But you do need water. You have to have water available, but the drier it is, the more value that adiabatic gas coolers have. Hey, John.
Hey, what's good? I'm great. Just how much water do these guys use, like in the course of a day? And obviously it would depend on, you know, relative humidity at the site. But,
Right.
You know, because I get asked that question a lot.
Yeah, I think it depends on the gas cooler manufacturer as well. Some have different, they use significantly less than a evaporative gas, thank you, an evaporative condenser, but I'm not sure exactly how many gallons. I don't know, Ignacio, if you have a better feel for that.
Well, I don't have a number, but the information from the manufacturers is about 80% less than evaporative condenser.
Okay.
So that's huge difference.
Yeah.
Think about that.
Okay.
80% less.
Yeah, yeah, it's significantly less, but there's a water use there, and of course, not just a water use, there's a drainage use too. Charge. Of course, we all see that on our bills. But that's kind of, so also the study that we did looked at 166 cities in the US. But for California, there's 5 climate zones that we identified using ASHRAE and IECC. So in our study, we classified them combining both. But you can see a dry gas cooler, there's no adiabatic along, 8,760 hours a year. In San Diego, you'd be running transcritical about 10% of the time, 870 hours a year. Whereas Palm Springs, I already showed you what that number is. And all the way down, there's quite a large percentage, but because some areas are drier than others, you go from 25% in Bishop to 0% if you had an adiabatic gas cooler. So dryness helps, and location helps, for sure. In Seattle, Washington, you wouldn't get the same benefit because there's so much moisture in the air already. The adiabatic, yes, will help you on peak demand days, but annualized, you're not going to see as much value as you would out of parallel compression, for example, which is a different kind of story. So this is a chart showing, from our study that we did, 13 different climate zones that we've identified in the Americas, actually. And the green boxes are the areas that had less than 30% relative humidity. And when you have less than 30% relative humidity, your annual savings were the best for using an adiabatic gas cooler in those areas. That's all I'm trying to point out. The other areas that had higher humidity, adiabatic wasn't as valuable. Okay. But from a peak perspective, that's not the one I wanted to show. What we're starting to hear more about, this was a gas cooler we had designed for our own training center in Canada. Because it's in Canada, we wanted to have split condensing. And split condensing is not something that's used a lot here in CO2 yet. In conversations with our Australian colleagues, because it gets really hot in parts of Australia, they're starting to install split gas coolers, not for the cold, for the heat. So it can handle those 45 degrees Celsius days, but when 80% of the other hours are not 45 degrees or more around 30, then they can split the gas cooler and manage the pressures better. We wanted 3 sections, only because we wanted to highlight it in our training center in Canada. But that's something that I think conversations are starting to build again in North America. On the study that I showed you, we looked at 100 different CO2 stores across the US. It was apparent that a lot of the cold ambient areas would have benefited from split condensing. Instead of having the gas cooler fans trying to manage it, you're down at 15%. You still want a bit of airflow on there, but it's so much airflow that now the high pressure valve's got to start backing pressure up instead of just letting the gas cooler manage it. So different conversations are happening around. We'll see where it goes. Yeah.
Are they pumping it out like a conventional system, or are they just using like a check valve? Are they actually physically pumping out all that CO2?
They're just leaving it there because it's 130 bar rated
No, I understand.
or higher. But yeah, they'll just naturally, but there's no hurry to drain it.
Yeah, I wouldn't think so, because like you'd be afraid like if you would open up a valve, and I guess that quick shock would be good for the gas cooler.
Right. Right now, that's what's being done, but it's not a lot of application so far. But they're talking about it. That's what I wanted to point out. In the E3 supervisory platform, we do have a split condenser because we've been doing it on HFC systems for years. So it's nothing really new. So this is kind of a low ambient operation kind of point here. Is of course when it gets colder out during extremely cold conditions, gas cooler capacity may be oversized, which we just finished talking about. And the fans are running at minimum speed, resulting in gas cooler condenser pressure becoming too low. When that gas cooler pressure temperature drops too low, you don't, below the flash tank, for example, if you weren't set up right, the refrigeration system can no longer stay in balance. If my flash tank pressure is lower, is because these gas cooler temperature set points were set too low, you'll fall out of balance. You'll get out of balance. So what's being used now more, we're hearing again more about, is 3-way diverting valves. Connecting now a 3-way diverting valve to bypass the gas cooler in a metered amount to make sure that when the pressures get too low, we start bypassing some of that hot gas around. Just like we've been doing pretty much on HFC systems, right? And this is kind of a setup here and a typical example. At 0 volt, you'd be 100% flow to the gas cooler. So if there's a problem with the power, then this 3-way valve would go straight to the gas cooler condenser. Maybe 5 volts, you'd be at 50%, and 10 volts signal would be 100% bypass. But there is a percentage, as it gets colder and colder out, and my minimum gas cooler outlet pressure is close to that point, that valve starts to energize and inject. And when it does that, though, remember that gas cooler outlet temperature sensor that's connected to my iPro? When it's time to bypass, that T1 becomes inactive. The iPro would switch to T2, so it gets a combination of gas cooler out temperature plus discharge gas temperature. You get a mix, and now the controlling sensor is T2. It's no longer T1. And if you want specifics about that, Brent Cheshire and Mike Hill's here. I'm not the guy, but they are the experts on exactly how that's done, what that switch point, what it looks like in the controller, and what drives it. But that's what's going on there.
Is that just a modulating valve, or is that going to be just a...
It's a modulating valve. Yeah, correct. Yeah. So let's see. Low ambient application, when the drop leg is below that minimum gas cooler outlet set point, fan speed should be at a minimum. The hot gas is bypassed around the condenser, or a portion thereof is bypassed around the condenser to keep the pressure in the flash tank from crashing. It's preferred to not cycle all the fans because when the gas cooler is cycling on and off, that rapid air really impacts these temperatures at the outlet. So keep that minimum fan speed on, and the high pressure valve will maintain that set pressure based on a subcooling set point. So that's important. The flash tank is, seems like just a tank. It's a receiver, right? It's a receiver, but it's also a flash tank. This is actually a picture of our own trainer. You'll see it out there. We have an oil level regulator. We've got various sight glasses, but you think it's just a vessel, but there is a lot that goes into engineering these things. I asked the question to one of our engineers that's on our systems team that's designed these things, and there's no small answer to how you design it. But typically there'll be, for my example, I'm saying 520, but it could be anywhere from 480 to 580, depends on the manufacturer, depends on the application. But stable flash tank pressure is really critical. And you think about any receiver pressure on any system you've ever worked on, if you can maintain a proper pressure here and liquid temperature and liquid quality, that means that valve is always seeing the same differential, the same enthalpy. It can manage and control superheat much tighter. That means if you got tight superheat control here, you've got tighter management coming back to the compressor. But if this pressure is going from 480 to 580, this valve is going to have to readjust all the time, which means the superheat's going up and down. It's continual readjustment mode. So the actual heat transfer through that evaporator is not as efficient. And now I've got compressors cycling on and off just because I've got 50 cases that are all seeing the same liquid quality changes over and over all day long because my flash tank, I can't seem to control it. And most likely you can't seem to control the flash tank because of this gas cooler outlet temperature sensor and interaction between the condenser control, the high pressure control. It needs to be stabilized for that flash tank to be stabilized. And there's a lot of things going on in here. You could be using this tank just as straight liquid. Of course, you've got a bypass gas valve coming off the top. You've got liquid coming off the bottom, going to a liquid filter dryer. You've got equalization lines going to an oil reservoir. You may be dumping more flash gas in that tank because you've got parallel compression and gas ejectors. There's a lot going on in that tank. And the connections at the top, you don't want them too low because you don't want liquid coming out the side. You want to pull vapor off the top to send to the compressors. There's a lot going on. And of course it's insulated because it's sitting at 36 degrees. So stable flash tank is really important. So I see here my high pressure valve, my bypass valve, and one thing about the bypass valve is that if I've got this flash tank set for 520, this bypass valve is there to relieve the pressure or build up pressure in the flash tank. So if my pressure is below set point, that valve will close off and won't let anything through to build that pressure up. But if it's higher than set point, it will open and pressure relieve the flash tank to my medium temp suction. So really important interaction, and that pressure transducer, which is connected to the iPro, is telling the valve driver where to position these valves based on flash tank pressure and gas cooler out pressure and gas cooler out temperature. On our unit, when you take a look at the unit, this happens to be my bypass valve because it's insulated coming off the flash tank and going to my medium temp suction. The Copeland valves are stainless steel valves with motor down. You can read the label when the motor is down for a reason because these are wetted motors. So the refrigerant cools the motor as it's operating. If that motor is up and it doesn't get the cooling, it's not going to have the life that you expect it to. You could have the motor on a horizontal, so you're getting some liquid in that motor for cooling. But that's just the position. So, interesting, 2 weeks ago, we had a field service guy, Copeland field service guy, sent me this picture of an inlet strainer of a Danfoss high pressure valve. And the point he was just kind of making that I want to make is that 100% of the mass flow of the system goes through that valve. 100%. Also, you've got these helical oil separators have a 3-micron screen in there. A lot of dirt gets trapped in there too. And then some of it gets through, it can get stuck in those inlet strainers. It's really important to make sure that these strainers get cleaned out. My little diagram over here on the left was just there to show low inlet head pressure does not produce as much flash gas for the same 520 in the flash tank as a high pressure. And that just makes sense, right? You've got 1,500 pounds, you need to drop it to 520. You've got a lot of energy transfer that has to occur. And a lot of energy transfer is a lot of flashing, because when you flash, you transfer energy and it pulls its temperature and pressure down when you transfer that energy. That's all I'm trying to show here with more white, more flash gas. The high pressure, like I said, this is the Copeland high pressure valve, but it's also the bypass valve. You can use it as an expansion valve for larger unit coolers. You can use it as a hot gas bypass valve, a suction valve, wherever you need flow modulation. The CV valve will manage that. And it's 10 to 100% capacity modulation. And we've just come up with another valve. The CV 4 to 6 is linear capacity per step. So every single step of that motor gives you the exact same capacity change. We've just launched another version of this valve, which is a non-linear curve, so that you have more smaller steps of graduation at the bottom end. So if you're around that 15, 20% open range, you've got less capacity change per step than the other valve. So you can have tighter control on low end is really the point. And this is, when you look at the trainer back there, you'll be able to identify the high pressure valve because the inlet is not insulated because it's gas cooler outlet pressure, stainless steel pipe coming into the inlet, and then this goes into the flash tank. The bypass valve, of course, is insulated inlet and outlet because it's coming off the top of the flash tank.
Andre, is that motor serviceable on that?
Not, it is not. That is a hermetic valve, yeah. Good question. So when you look at the setup of a high pressure and bypass valve, I've got my iPro high pressure control, and all of the algorithms for high pressure control is in the guy on the left. That's the controller. That's all the brains are in that control. The one on the right is the driver. So it tells the valves, where to position itself. So at home, I'm the gray side here, and my wife's the white one. So my pressure transducer is not showing very well here. I should have moved it. It's on the wrong spot, but there's a pressure transducer here, one here, and a gas cooler outlet temperature sensor. When you're operating in subcritical mode, 87.8 degrees below that, the iPro manages a subcooling set point of 5 degrees. That's what it's doing. And when we're above 87.8, now you're measuring to an optimized COP set point. There's actually a library inside the control that says, okay, at a given discharge or gas cooler outlet pressure of 1,300 pounds, you need to be, X amount of temperature, so it's 90-degree temperature. There's a table in there that it said at 90 degree, you need to be at this pressure. So the iPro will move to that pressure because it's the optimal COP optimal point of efficiency in transcritical. And they all kind of work that way. All the manufacturers work that way. So when you combine those two together, we've got gas cooler pressure and temperature and flash tank pressure. That's what it's measuring, gas cooler pressure and temperature. So now we've got a high pressure valve and a bypass valve that's connected to. So the driver I mentioned is connected to these two valves. I talked about the subcritical mode, measuring 5 degrees of subcooling in transcritical mode. I'll show you what that table is in a few minutes. It optimizes COP and supercritical mode, as I mentioned. There's also a heat reclaim mode feature. Of course, more and more end users want heat reclaim, and of course in California, part of Title 24, you have to have heat reclaim on a supermarket system. So there's a feature for that built into the iPro. And it is integrated into the E3 for visibility. And that same note here I put, condenser minimum pressure set point must be higher than the iPro's minimum set point. And if they're reversed, they will fight each other. The fans will fight the iPro. Yeah.
It's almost like a fan cycling, fighting the whole back.
Right. Yeah. Yeah, because we want to make sure there's a gap there in between it, so they're not fighting each other. And that's just a basic layout. T1 is considered my temperature 1 at the outlet of the gas cooler, the one I talked about being extremely important. P1 is the pressure transducer gas cooler outlet feeding our iPro controller. And then P2 is my pressure transducer on the liquid receiver flash tank. And I've talked about some of these things already, so I'm not going to kind of go through that again. But one thing at the bottom end here, flash tank pressure, if the flash tank pressure is above the high pressure limit, the high pressure will start to close. The high pressure valve will start to close and decrease the pressure in the flash tank. If the pressure in the flash tank is below the low pressure limit, the high pressure valve will start to open. So we don't want the flash tank to be too low a pressure. So if we back up, if my flash tank pressure is too high, above my 520, there's a high limit and a low limit. So we're trying to maintain 520, but there's a high limit, might be 580, and a low limit, whatever that happens to be dialed into. So when it reaches that high limit, the valve will close, and even if it backs up pressures in the gas coolers, well, that's what's going to happen. That's okay, because it needs to drop that flash tank pressure. And in reverse, if my flash tank pressure is too low, it will open to try to pressurize it more, and that bypass valve will be starting to close off as well to try to build that pressure up. And this is happening all the time. Always movement. This is a driver I mentioned, 24-volt supply, and the driver, valve driver as well as the iPro they have their separate their power supply as well. No, you don't want to be sharing it. It's an ungrounded Class 2 transformer. And the other thing that's important to have, and more OEMs are adding this back on, this is called a visiograph. It's a local screen that's in real time with the iPro, high pressure control. If you don't have that, you have to wait for the communication to go to the E3 and then back to the valves. If you have that, it's in real time. Right there on the rack, you can see what the valves are doing immediately. If you're just using the E3, there's a delay. So just keep that in mind when you're troubleshooting. Because you can see the position of the iPro, the high pressure valve, the bypass valve, the flash tank pressures, all of that through that visiograph, we call it. And this is the COP set points I talked about, the table. So when you're operating in transcritical mode and we're at 93 degrees, or 96 degrees, excuse me, Fahrenheit, the valve will position, the high pressure valve will position itself to about 1,350 pounds. If I'm at 104 degree gas cooler outlet, it's going to go to 1511. Those are not configurable. Those are in the control. You can't change those. That's one thing. And that would be position 2 on the pressure enthalpy diagram here. So the optimum position based on the load demand on a given point in time would be point 2 that would reference this table. Something that's unique though about CO2, if a bus load of people show up in the supermarket and everybody goes to the cases and open up all the doors and add all kinds of load very, very quickly, and the suction pressure starts to rise, and you're still within the compressor envelope, the high pressure valve can temporarily increase head pressure. By increasing the head pressure and still leaving the gas cooler at 104 degrees, look what happens. I get that many more BTUs per pound. I can pull that extra temporary heat load increase out of those cases. It's going to cost me energy to do so. But once the suction pressure settles back down, then it will revert back to its optimum COP point. If it stays within the compressor envelope, then it can drive the head pressures up to get more capacity temporarily. And you can view that through the E3, all of the data, the high pressure valve, the percentage open, and so on and so forth. So it's a good troubleshooting to have it connected to it. I'm running out of time, so I'm going to go right to oil systems here. You got till 9, right? Yeah. So the last thing I want to kind of point out here is a bit of an example, if you will, of subcooling set point. So let me just double check here and say, example, when a system is operating at 60 degree gas cooler out, so that temperature sensor is 60 degrees, okay? 60 degree gas cooler out is equivalent to a saturation pressure of 733 pounds. And I said that when we're operating in subcritical mode, we're trying to maintain 5 degrees of subcooling. So what happens here is the iPro senses that 60 degree gas cooler out. It knows what pressure the saturation pressure is. So what it'll do is it'll start closing that valve to get 784 pounds. Because saturation means temperature and pressure are equal. There's 2 ways I can get subcooling. I can cool the fluid, or I can raise its pressure. Either way, I can get 5 degree delta between saturation and actual. So in this system, the iPro high pressure valve closes to drive the head pressure up to throw it into a subcooled range. That's how it manages it. Because we can't cool it anymore, but we can change the pressure. So that's how it's managing its subcooling. On the high side, and I mentioned, as I already talked about, as this flash tank pressure increases or decreases, the bypass valve and the high pressure valve start to move. One thing that I want to point out here on this chart before I move to the next one is my oil reservoir, 520 pounds, is equalized to my flash tank, 520 pounds, right? So if this flash tank goes to 580, that will go to 580, right? Eventually they'll go up to 580. If this drops to 480, that'll drop to 480. If my suction pressure is floating, and now instead of 410, maybe I've got 440 or 450 suction, and I've got only 480 in my reservoir because my flash tank pressure is down. What happens to the differential between my oil reservoir and my compressor, the feed to that compressor. I used to have a 100-pound differential pushing oil into that compressor. Now, because of system conditions, geez, I only have 50-pound differential or 40-pound differential. And you might be wondering, it's asking for oil, but it's alarming because it can't fill it fast enough. What's going on? I don't understand. Why is all of a sudden it's not filling fast enough? Then you got to go back and figure out, is there something, did something happen to my flash tank pressures that could have influenced my receiver pressures? Did something happen to my suction pressures as well? And everything in combination adds up to not enough pressure to feed the compressor fast enough in 120 seconds. Those are things kind of ask yourself when you're going through it. And I've got another example that I could show, I could talk to. So we're going to talk about the oil system. Oil separator right at the outlet of my compressor, of course. I've got ball valves, solenoid valves, differential valves to help reduce that pressure. I'm feeding in this particular example through a cycle. I put a sight glass only because our unit has a sight glass. A filter dryer, super important, large filter dryer, and feeding both compressors. That scenario I talked about, low differential for medium temp compressor, even if I've got 480 pounds here, it's not going to affect my low temp compressors because I got 200 pounds there. I got lots of differential on my low temp compressor. It's the medium temp that you may be asking about, okay? And some will put heaters around the reservoir, especially there's a lot more outdoor units these days. Make sure that that oil stays nice and fluid and not too viscous. But that's important. And the other thing, of course, is that in an oil separator, 100% of the mass flow goes through that oil separator. Yeah.
The purpose of the regulator, to knock it down before it goes in there, is that to reduce the amount of power that you put in the flash tank? Because if you were just dump 1740, it would have to vent off whatever made the flash tank.
Too much.
So it's there to knock it down to reduce that load, correct?
Right. Yeah. Outlet pressure regulator to make sure that this pressure on the outlet is maintained to a certain amount. And it's aided by the equalization. Yeah. So you do have all that mass flow going through here. Of course, when it gets to a certain level, and I've got another slide, we can kind of look at it a little easier on this particular slide. The basic system, this is out of a Temp-Right book. I could have taken it out of a Westermeyer or anybody else's, but discharge gas comes in and you can see that coalescent filter here going off into the discharge. And when you get to a specific oil level, it's time to drain the oil. Typically there's a solenoid valve in here that'll energize and allow that discharge pressure to push oil into that reservoir. Keep the terminology, it's not, some people call it receiver. If you call it receiver, you'll get confused in your conversation with the flash tank. If you say reservoir, it's an oil reservoir, then we all understand what you're talking about when you're referring to something. On our system, we have a medium temp oil separator. We typically run around 1,200 pounds. You'll see the unit running around 1,200 pounds. This is transcritical mode. Going through a valve, a solenoid valve. Up in here, our pressure reducing valve. And then it goes up into our oil reservoir. That's our normal flow. When we need oil, for the compressors, oil comes out through this oil line, through a large filter dryer. It's a filter dryer made specifically for oil lines. 100% molecular sieve, which is targeting moisture, not acids. And there's a 3-micron filter pad in there. So you want a lot of filtration because, you know, these separators are over 98% efficient. So a lot of the oil stays within that circuit. And one thing about CO2, just refrigerants and oil, when there's moisture in them, moisture always tries to find an equilibrium between refrigerant and oil. So there's going to be a percentage of moisture traveling with that refrigerant. So drying it here and filtering it is super efficient. It's good for our compressors, so that's why, of course, we promote that. These oil separators are designed to, over 2,000 pounds pressure, 98% efficient, 98.5% efficient. And they're there to trap the oil so it doesn't circulate out into the system and impact heat transfer surfaces as much as possible. But one thing's important, because 100% of the mass flow goes through them, I'm sure you guys have probably seen that these filters will break apart if they load up with dirt on startup. They should be changed within 24 hours. And recommended pressure drops may change a bit, but around 12 to 13 pound pressure drop from inlet to outlet tells you that this thing is loading up with dirt. It's time to change it. And you could use pressure transducers that are already on the system to measure differential. Westenmeyer came up with this device that actually zeroes out these two transducers against each other. So you are measuring a net differential pressure. Instead of using two transducers that are already on the system that have a plus minus 1 or 2% on 1,000 pounds or 2,000 pounds, could be beyond the 12 pounds already. So one thing, we're testing that at our CO2 lab, at Copeland lab in Sydney, Ohio, just to make sure, the differences. But anyway, there are tools out there to help you through that process. So the oil separator, of course, separates the oil from the discharge gas, as I talked about. And this is just the same kind of system showing here. A typical oil reservoir is equalized to the flash tank I talked about. If the flash tank is 520 and the crankcase is 410, that means the differential oil pressure going to my compressors is sufficient. Should oil differential pressure fall below 50 psi, it may not fill the compressor in 120 seconds. And that's what I was talking about, because there's a 120-second timer in there, right? This can occur if the flash tank pressure is low and the reservoir pressure with an increase in medium temp suction, like I talked about. So as your reservoir pressure starts to drop, maybe you're floating your suction up, your differential can be reduced. So I talked about this already. It's about 3 microns filtration, and you can see it filters first, goes through that filter pad, metal screen, and 100% molecular sieve desiccant for moisture. And these are just the oil controls. I showed 2 here, the OMB, Copeland OMB, and the Copeland OM5. This is a European version that is currently being UL approved. Right now it's not, but is currently being UL approved. And how they really work is within the green zone, you're going to be green, your oil level's good. When the oil level, the float, there's a Hall's effect magnet in there, I'll show you in a sec. When that gets too low, you're into a yellow zone, the yellow light comes on. When you drop below that 25% line, then you get into a red zone, and you got a 120-second count. That starts from there, and that's what I was talking about, that 120-second count. There's also a tube that is connected to these. Some are already connected, some you've got to screw it on there, because there's an adapter that goes from the oil control adapter into the compressor. So when it feeds, you want to put that adapter in there to make sure that oil gets out into the crank of the compressor. So that's important. They measure based on a Hall's effect sensor, and the actual magnetic portion is in the inside wall of the device, and the float has a sensor on the circular part. So as it's measuring, the sensors are measuring its position, and that's how it does it in there. So making sure that the control is level is also important. Don't stick that on the compressor, crooked. So that's important. So oil pressure, we talked a bit about that, reducing oil alarms, and I've talked about this already, connecting to the oil control here. Here you're running somewhere around 200 pounds in the crankcase. Here you're somewhere around 400 pounds in the crankcase. So at 520, you've got lots of differential in order for oil to flow. One thing to note, oil flow does vary with differential. This is our control, but everyone has their own charts. If I was to unhide this slide, I got the Henry chart right next to it, hidden beside it. But what I'm trying to point out here is this is our Copeland semi-hermetic CO2 medium temp compressor. The 6 smallest versions have 61 ounces of oil in them, and the largest models have 95 ounces. And really that's midway through that sight glass. That's really what the volume of oil is, okay? And scrolls are 32, 48, and 64. If I've got 110 pounds MOPD, so that's pressure differential across it. If I've got 110 pounds of pressure differential, it will fill at 35 ounces per minute. 35 ounces would mean that, you know, the top compressors are half full, and that's not even going to happen because, you know, it only starts to fill when the glass, and look how high the glass is. So there's still a lot of oil below there. But nonetheless, as you start losing differential, you're down to about 50 pounds, your flow rate's just reduced by 50%. So what maybe took 100 seconds before is going to take you 200 seconds, and 200 seconds is beyond the 120, so you could get an alarm. Okay? That's all I'm trying to point out here, is an actual chart that shows you volume flow rates diminish with pressure drop reduction. Okay? Yeah?
Does anybody not control that reservoir pressure or the regulator and vent and suction instead of the flash tank? And guarantee you're going to have the exact pressure you want?
I missed the first part.
Does anybody control the reservoir pressure or the inlet regulator at all to fix it where you want it and not let it float in wherever the flash tank goes? So you can guarantee there's pressure.
I'm not sure, to be honest with you.
On Bitzer's stuff, they actually show a regulator like that. So I mean, it has been done.
Yeah. I have to check with,
Seems like a real critical thing, maintain that exact peak pressure you want.
it can be.
But it forces you to tune the flash tank, it forces you to tune the suction, so those two don't get out of whack, so you maintain that differential.
Yeah. Yep. No, that's a good point. The other thing I also wanted to point out is the difference between a high pressure oil system and a low pressure oil system, because we're starting to hear more about high pressure oil systems. On a low pressure oil system, that's what I've been talking about. You got a pressure relief here of 1740, and I'm operating up to 1,600 pounds. But my oil reservoir that is, you know, equalized to my flash tank is at a 650 pressure relief, right? Because it's equalized. And so I'm not going to get, so I'm going to be 520 pounds in here feeding. But on a high pressure oil system, I don't have this pressure reducing valve. I'm not equalized to the flash tank. You've got discharge pressure in that reservoir. You got lots of pressure available. So that means that this oil control has to be able to handle 130 bar, not just 130 bar, huge differentials. 1,450 pounds of differential, 100 bar. So that one's got to be rated, and even that one, because if I got 1,500 pounds and I got 200 pounds in here, I got 1,300 pounds of oil differential. So that control better be able to handle that. And it does. They're rated for it.
So obviously they're using two different controls on the
Yeah.
low temp and, or excuse me, not low temp, low pressure and high pressure, right?
Yeah.
So is that an OMC on the left and an OM5 on the right? Or what control is that?
No, this could be OMC. OMC is rated to 130 bar and 100 bar differential. The OM5 as well that we're getting UL approved, and others have 100 bar differential. The OM, have you ever heard of the OMB? The OMB can be used on medium temp because it's 60 bar rated, very low, much lower, but 60 bar is way above 45 bar pressure relief on the low. So if you're ever stuck, you can't get an OMC or you can use an OMB as long as you're on a low pressure system, not a high. Yeah, knowing that can get you out of trouble, for sure, because OMBs are in stock everywhere. Yeah, they are, but that did happen because there was a bit of a shortage. The other thing to note, though, when we are talking about high pressure oil system, if your coil is 10% off, you could lose 20 bar or 300 pounds of differential, because that solenoid valve now has to overcome that differential. So if the voltage isn't right, you lose the ability to pull that plunger off the seat. So these are all little things that you may not think about, but if you do have a high oil system and you're on the low temp, would be the low temp, why is that thing not even opening? You might want to check the voltage on the coil. Little things like that. And the last thing, standstill pressures. Those are top of mind with retailers today. Obviously, because at 68 degrees Fahrenheit, we're at 815 pounds. So if a system loses power and it only averages out to 68 pounds, that's 815 pounds. That's way above what your pressure reliefs are for 650. So that's something to consider. Those tanks sitting here right now at the back, they're sitting with 815 pounds in them. So that's also important when you go to charge a system that's got a 650 pressure relief. Be aware that you don't want to crank that valve open too wide because you'll blow your pressure relief, at least starting off the charge. As more refrigerant comes in, it cools down and it lowers. But
what's the relief on the tanks? Because I heard people saying that if people leave tanks out in the sunlight, they end up not having as much CO2 on hand as what they thought, only because they're constantly relieving at a certain pressure.
there are tanks that have burp valves on them. The restaurants, I don't know that these valves have burp valves on them. The 350, there's big, large ones that sit outside the restaurant. You'll hear those burp away. Or if you're on the highway, you're behind a big truck, you'll hear it burp away, and it'll be a note on it to tell you this may be burping. But there's pressure reliefs anywhere from 1,600, 110 bar to 120 bar on the high side. Like I already mentioned, 650 on the medium temp side these days, and all of these pressure reliefs are vented to the atmosphere, as you guys probably already know, except for the compressors. But in Canada, all these compressor pressure reliefs that are on there, even though they're 135 or 140 bar, they're all being manifolded and in pressure relief to the outdoors as well. Something I ran across just recently that'll be available this year, I thought was pretty cool. You've got the three-way valve, ruptured disc in the center, and then the pressure relief on the end. And they come in kits of different pressures, which I thought was kind of interesting because we ran into an issue with pressure relief valves leaking at one of the sites that we were working at. We were wondering, why are we always losing gas? And the pressure relief valve was just leaking. We actually had to go back and put ruptured discs in there to prevent that small leak from occurring. Of course, when the ruptured disc goes, it'll be indicated by the dial, and then you can get up and change it. So, other ways of mitigating pressure leaks, is condensing units with a plate heat exchanger. Sometimes they have heat exchangers inside the flash tank, or there's a plate heat exchanger. And by thermal siphon, when the system cycles off, The unit is powered by a UPS and will turn on in order to mitigate the pressures in the tank. You know, thermosiphon, you get 1.8 degree delta, you get 10 psi of pressure differential. So, that's why it moves so free. You know, 7 degrees gives you about 40 pounds. So. And also burp valve, you talked about burp valve. Sometimes you can hook up a generator to your controller, and as you approach your 650 pressure relief, you burp a solenoid valve or an electronic valve to relieve the pressure in the flash tank. It drops, and then when it comes up again, you just burp it. So you're not losing large amounts. You don't have a leak event, but you are managing the pressure. And understanding where your codes are for pressure reliefs, how far off the roof you're allowed to have them, is going to be important depending on where you are. This happened to be a site in Canada where they're 15 feet off the roof, which is ridiculous because you got to get on a ladder to change a pressure relief, but every jurisdiction's a little bit different. So that's it.